Looking at this split screen, the left side shows a common reality for early programmers, a terminal crashing with a segmentation fault. On the right is a stable, optimized application. The difference between writing code that crashes and code that scales comes down to how you handle physical memory. This 3D grid represents your computer's physical memory. When you define a variable, like an integer holding the number 5, it physically resides in a specific location. Here, it sits neatly in a memory box at the exact address of hex 200. To navigate, link, and safely hijack these physical memory boxes, C++ gives us 4 specific tools: the asterisk, the ampersand, the arrow, and the double ampersand. Understanding how these operators manipulate the physical grid allows you to predict exactly how your code uses hardware, moving past the guesswork of abstract syntax. The asterisk is the pointer operator. Declaring a pointer creates a distinct box at address 100, storing the address of box 200. This creates a raw path. Dereferencing activates this path, traveling down the line to manipulate raw memory at the final destination. At address 300, the ampersand reference operator attaches a heavy chain and label directly to the existing box, creating an alias. Passing variables by reference lets functions hook the original data. This guarantees null-null safety and avoids massive copying speed penalties. So, pointers give you raw control by building distinct paths, while references guarantee safety and speed by chaining directly to existing memory. For heap data structures, the arrow operator combines pointing and accessing via a hidden 2-step mechanism. First, it dereferences the pointer at address 500, following the path to the heap node. Second, it executes member access, sliding open the data compartment to drop the value inside. Modern C++ practice relies on smart pointers to manage these heap allocations. They overload this exact arrow operator, meaning you can traverse complex memory structures easily, while the system quietly handles cleanup in the background. Let's test this. Starting at the head node, how would you access the data of the third connected node? You follow the chain: head, arrow next, arrow next, arrow data. Navigating linked lists, binary trees, or any object-oriented heap memory requires you to master this 2-step arrow traversal. As you move toward writing extreme high-performance C++, you have to handle temporary data without wasting processing power. This requires the newest of the 4 tools, move semantics, via the double ampersand. Applying the move function to this string box engages a purple gear, creating an R-value reference. The dashed line signals intent to extract. During transfer, internal pointers are hijacked completely. Contents move into the new function box, leaving the original as an empty shell. The performance implications here are massive. If a function returns a vector with 10,000 elements, you no longer allocate new memory to copy them. The system simply steals the internal pointer, transferring all 10,000 elements instantly. The double ampersand gives you the power to break the default habit of copying data, allowing you to safely transfer ownership of massive resources exactly when you need to. Now we combine these operators into a real-world workflow. A senior engineer will routinely take ownership of a newly created heap node and immediately link it into an existing data chain. Watch the tools work together. The double ampersand reaches out and grabs the new heap node, transferring ownership into a smart pointer. Instantly, the arrow operator engages its 2-step mechanism to lock that node's pointer securely into the existing structure. Here is your final visual blueprint. The single asterisk builds raw access paths. The single ampersand creates safe physical aliases. The arrow handles 2-step heap traversal, and the double ampersand executes fast resource transfers. To solidify this, try implementing a simple linked list using these specific blueprints. Practicing these low-level interactions provides the intuition necessary to debug and optimize complex systems effectively.